Okay, now we're going to switch gears slightly. We have two plates, two metal plates, each with area 10 square meters. So each one would be about a little over 3 meters by 3 meters, about 10 feet by 10 feet. Just to get the scale. Okay, and they're separated by 3 millimeters. And we assume that we have a charge of 4 microcoulombs, or not, 4 microcoulombs on each plate. So we could achieve that by putting a battery of appropriate size, attaching one terminal to this plate, the other terminal to this plate, and pulling charge off of this plate, putting it onto this plate. Pulling negative charges off of this plate, pushing them onto this plate, as would be the case if we use what we usually use is metal wires. Okay. Now we want to calculate a number of things. First of all, we want to calculate the resulting electric field between these plates. Now, just making reference to what we should understand perfectly well, electric field is flux over area. I didn't bother to put the magnitude signs on there. And for a large plane charge, except near the edges, and by near the edges, in this case, I mean basically something that's something that's at least a few times this separation from the edge, which is not far. So at 10 millimeters from the edge, this would be a very good approximation to the field. Near the edge, of course, we get edge effects, and we don't worry about those, at least as a first approximation. Okay. So electric field is flux over area. You recall that we do a cylindrical or rectangular tube or box running on both sides of the charge distribution, or the plate, in this case, the flat charge distribution, the plane distribution. And we have field penetrating both ends of this box or cylinder. So the area that's being penetrated is double the area enclosed, double the area of the plate enclosed by the box. The charge enclosed is sigma times A, where sigma is the charge per unit area and A is the area that we enclose. And we divide that out and we find that the field is 2 pi k sigma, as long as the ends of this box are not so far away that they're not much further from the edge than from the nearest point of the plate. Okay, so we have a field for the electric field of a single plate. Now, what's the charge density of either of these plates? Well, charge density of the positive plate would be plus 4 times 10 to the negative 6 coulombs divided by 10 meters squared. That's the charge per unit area. The area of the plate, we divide the total charge on the plate by the area of the plate. We get our charge density sigma, area density. And that comes out 4 times 10 to the negative 7th coulombs per meter squared. Now it follows that the electric field of one plate then is, you're just doing 2 pi k sigma, it's 2 pi, k is 9 times 10 to the 9th Newton meter squared per coulomb squared, and we multiply that by our 4 times 10 to the negative 7th coulomb per square meter sigma, and we end up with something close, and you can check my arithmetic, and especially check my powers of 10. If I make a mistake, I expect you to find it and correct it. I think we get something pretty close to 2.4 times 10 to the 4th newtons per coulomb. So that the electric field between the capacitor plates, and this is a capacitor, the electric field between these plates is going to be double that. And we talked about why that would be previously. The field is away from the positively charged plate and toward the negatively charged plate, so that we have for both plates, in between the plates, the field is in the direction from the positive plate toward the negative plate. Those fields reinforce, doubling the field that we get, magnitude of the field we get from one plate. So here's the field. Twice this is twice 2.4 is 4.8. We have 4.8 times 10 to the fourth newtons per coulomb. And that's the same, and you should be very familiar with the way the units work out. Keep working at them until you are 4.8 times 10 to the fourth volts per meter. The next question then is, what's the voltage between these plates? And the voltage between the plates is just the electric field dotted with the delta X between 2 points. We take the electric field dot with the displacement between the plates. In this case, the electric field is your 4.8 times 10 to the fourth volts per meter. The separation is 0.003 meters, so that the voltage between the plates is the product here. And that comes out, I believe, 144 volts. Check my decimal point on that. I had it as 14.4. Decided that no, we got a 10 to the square. There's 144. Okay. Then asked to do the capacitance, which is the charge divided by the voltage. So what's the charge divided by the voltage? Well, the charge on a plate is 4 microcoulombs. The voltage is 144 volts. If we divide that, we end up with, I believe, 3 times 10 to the negative 8 coulombs per volt, which would be 30 nanocoulombs per volt. And I started to write that out here, and I can't write it down that low. But that turns out to be 30 nanofarads, so that 30 nanocoulombs per volt is 30 nanofarads. And that's the capacitance of this capacitor. We also ask what happens if you shrink this 3 millimeters. Okay, if you shrink the 3 millimeters, what does this change in the calculation? It doesn't change sigma. Now, it would change sigma if you had the same battery there, but when it's discharged, with the condition that you have 4 microcoulombs on each plate, plus one, negative on the other, it doesn't change the electric field. Doesn't change the electric field of the capacitor. So let's see, what does it change? Well, it changes the delta X. It changes the separation is your delta X. Your delta X is going to shrink down to 1 millimeter. What does that do? Well, that makes this number 3 times smaller, so you only have 1/3 the voltage. Having 1/3 the voltage, you're going to get 3 times the capacitance. You get the same charge for less voltage. So by moving the plates of the capacitor closer together, you increase its capacitance, which is the amount of charge it holds per given voltage.